Our next speaker is Chris Walsh. Chris is a third-year PhD student from the Beatson Institute under Rob Insall and Joanne Edwards. His project uses deep learning to investigate how the patterns of cells at the edges of tumors will allow us to understand whether tumors are spreading or benign. And this work will help patients by making cancer pathology faster and more efficient. He has actually presented his work on tumor blood detection at one of our very first colloquia back in 2020. So I'm very interested to see how you improved your work.
Enjoyable. So I want to talk a bit about my work ensuring accuracy in reproduction in virtual immunohistochemistry. So we'll get into what that means in just a second. But I should talk a bit about the people that are involved in this project. Like Beatson said, I'm a PhD student in my third year, but my supervisors are Professor Robert Insall, who's a Professor of Mathematical and Computational Biology. So he's got a nice, he's got his feet in both the deep learning side of things as well as the biology. And Professor Joanne Edwards is a Professor of Translational Cancer Pathology at the Institute of Cancer Sciences. No worries. Yeah. So she's very much, an expert in pathology. So between the two of them, I've got a nice, wide knowledge base to. Yeah, no worries. Sure. So like I was saying, between the two of them, I've got a nice, very knowledge between deep learning and pathology to draw on. So that's been fantastic throughout my PhD now. All very thanks to both of them for that. So, let's start working there. There we go. So let's talk about pathology. So if you unfortunately have cancer or you're suspected of having cancer, the first thing we'll probably do is biopsy to try and determine, what type of cancer it is. So these are analysed usually by taking a slice of the tissue and putting it under a microscope. But in order to analyse the tissue structure, you've got to take a really thin slice and it ends up being transparent. To make it visible under the microscope, one of the first things you've got to do is apply a stain to it. And the most common stain in pathology is one called hematoxylin eosin. It's this pink and purple one you'll see right. I'll get a bit more detail in a minute. And it's been around for over 100 years. It's been around for a long time, but it's still the gold standard stain in modern pathology because it works well basically and it's cheap and easy to apply. I should also say that it's applied as part of standard reporting in nearly every single patient. So anyone that gets a biopsy will probably have an HN stain done. But there's a problem because it indiscriminately stains both tumour and non-tumour cells. So what I mean by that is if you, this is like I say, an example of one of these HN biopsies. And you can see maybe here, this is tumour core, and I'll outline this in a minute. But there's also non-tumour cells and what's called the stroma surrounding this. And then a pathologist is doing their analysis to try and determine what cancer it is, how far it's spread, etc. They need to, look at that boundary, look at what cells are in it, just like the blending was saying, one of the main parts of my PhD project has been the detection of tumour blood scoring. What we also make the detection of tumour blood to do tumour blood scoring. So that's the process of looking at these little individual tumour cells and the density of them. But like I say, a pathologist got to do something like this, look at the invasive margin of the tumour and try and pick out where that begins and ends and what kind of, how far the tumour spread and other, the other cell morphological features as well. So my point is that it's hard to do this on H&E alone, but once pathologists are well trained, they become quite expert at it. But even then, it can be hard to distinguish one cell type from another without more advanced methods. So that's what I want to talk about. There's obviously solutions to this in modern pathology, and one of these is immunohistochemistry. So that's the process of visualizing an antigen-antibody reaction, and what that means is every tumor can express a specific antigen that you can design an antibody to target and attach chromogen which colours that antibody so that it kind of lights up the tumor tissue. So this is that same section as before in H&E, and if we transform that to the IHC stain for this particular cancer, colorectal cancer, you can see just that now you can see the tumor structure. And most importantly, all these little individual tumour cells that are starting to pop out to surround it so that the pathologist can count the density of them and make a diagnosis. So you can see just how much more accurate and indeed how much less work it is for the pathologist and the time saving impact from looking at this compared to an H&E. So the problem with IHC is it's complex and it consumes more tissue and resources to do and requires special labs and equipment, so it's not done as default for every patient, only when you get a particularly complex case that may require more advanced analysis. So this suggests to me that there's a need for a more accessible and economical method to improve to attain this improved level of contrast that can be done for every patient and is easily accessible. So that's been one of the goals of my PhD project, is essentially to create a virtual method of converting between these H&E stains, which are done for every patient and are readily accessible, and these more digestible for human eye IHC stains. So how have we started to go about this? Well, there's been actually, there's been quite a lot done in this area, and most of it's with generative adversarial networks, because obviously we need a method of image synthesis for this virtual IHC staining. And GANs have become, a kind of gold standard in image generation over the last decade. Essentially, something that the first one was released in the first GAN was 2014, I think. So been out for a while now, but even now they're an exciting and rapidly changing field, and we've got a huge number of applications, from photorealistic fabrication of objects and scenes, and map generation of satellite, generation of maps from satellite photos, and image-to-image translation in terms of scene translation, which is why they're key to my work. So just to show you how powerful they are, or they've gotten, in case you haven't seen anything that any of these deep fake cell things, have a look at these two images and can you tell which of these people are real and which is a generated one. I'll give you a second or two to try and guess before reveal the answer, but turns out that this person here is indeed, or didn't exist, or never existed. There's a really fun website called thispersondoesnotexist.com where you can go and see randomly generated humans that have never been. And this is the real human, Amy Webb, who's a futurist, which I thought was appropriate for the conference today. So you can see just how powerful GANs have gotten and how hopefully we can apply them in this powerful medical data. So as a quick overview of how they work, they're essentially actually 2D networks that are drawn together. So the first, and that is the plot in blue, is it's typically called a generator, and that's a type deep network that takes in an image and or takes an image or random numbers and generates another image. So for our application, it would tend to be takes in an H&E image and translates it to an IHC image. But the key for GANs is that they're coupled with another network, which is often termed a discriminator, which takes in a real image and tries to discriminate between the real image and the generated image. And so these are trained together in opposition. It's often called adversarial training. And by competing against each other, they each become better at their specific task, where the generator becomes more advanced at using realistic and lifelike images, and the discriminator becomes more advanced at picking up the fakes. So how do we work to apply them to pathology, specifically our image translation task? Well, unfortunately, the standard GAN has a pretty big flaw when used for stain translation, because they can potentially fabricate, inaccurate structures that never really existed and then put H in the image. So if I expand this a bit, you can see in these, the first column is the H&E image, the middle column is the real pantype keratin for that, the pantype keratin IHC image for that tissue, and on the right is an output from just a standard GAN. And you can see that if you look closely, particularly here, you can see this, these glands have been changed entirely here. This one is just, it's kind of tiled, something that looks like cell nuclei across the whole tumor core. And this one's a bit better, but again, it's changing the cellular structure in many nuclei, which is obviously absolutely useful for pathology, even though the images are very lifelike and might even, some of them might even feel pathologists. But this is obviously a significant liability for medical use because the diagnosis critically depends on that cellular structure. So how do we go about overcoming this? Well, Luckily, just a few years ago, there's a paper published by Zhu et al. In Berkeley about, it's called, on a type of network called a cyclogan. And this is a method of cell translation that maintains structure throughout the process, which is key for us. And you can see the original paper shows lots of different applications, like converting paintings to photos and papers to horses and summer to winter, and all sorts of cool style translation tasks, which is really good. So we thought we would give this a try for our translation task. And how a cyclogan works is essentially it's now two GANs joined together basically, where the left-hand side is your generator discriminator pair just as before, which takes in your H&E and outputs an inferred plastic pattern for our IHC image for our task. But the key part for a cyclogan is it's also got another GAN appended to the other side, which does the reverse, so it converts back from the IHC image back to an H&E one. And why this is important is because if you take this generated H&E based on the generated IHC image and force the network to make it similar as possible to the original H&E through this amendment to the loss function called cycle loss, it must enforce the structural detail throughout this whole, this path through these two generators, because obviously for the structural detail to be present in this image, it has to be present in the inputs of the generator. So this is really cool because it means that the cyclogan must enforce the structural detail throughout the whole process. And most importantly, in this generator, where we're generating our virtual IHC images. This is pretty cool. So how do they work when we just feed in our data? Well, they do indeed enforce the structural detail, but that's not quite the end of the story because, as you can maybe see over here, some of it's hidden, but they do a great job at preserving the cellular structure. It's identical to the input H&E images, but this time they don't preserve the stain, which is obviously one of the most important tasks as well when we're trying to do virtual restaining. So that's the second thing, if you remember from the talk today, is that they're great for structural reproduction, but it's not the end of the story. You need to modify them a bit to get it to work. So that's what we've been working on for the last little bit. And we found that you can indeed modify a cyclogan to get it to balance the focus between stain accuracy and structural reproduction. And this is how we do it. So this time it's a cyclogan set up similarly to before, but in addition to preserving the structural loss through cycle loss, we've amended another term for the cyclogan loss function that we're calling mid-cycle loss. We are, in addition to constraining this inferred H&E patch to be similar as possible to the real one, you constrain the inferred IHC patch in the middle of the cycle to be as similar as possible to the real IHC patch. And we've appended weighting terms so that you can balance the network between preserving the structural detail and preserving the stain accuracy. And we've evaluated our method using a variety of techniques. So the first one is maybe a bit unique, so I'll cover that, and that's called the staining index coefficient. And basically what we do is color deconvolution to separate the generated images into brown and blue, which is the anti-parent stain, the Immunohistochemistry background, and then compare this to the real patches to see how well they overlap. And what we found is that by the addition of mid-cycle loss improves the accuracy for both stains. And then you can also look at the realism of the image by evaluating the Gaussian inception distance. And we found that the mid-cycle loss makes images more realistic as well, obviously by improving that stain accuracy. So how does it look in application when you apply it to real slides? Well, here you can see one of our best performing model converting that H&E image into a virtual anti-keratin stain. You can see now it exactly preserves the structure, but also most importantly it applies the correct stain both to the tumour core and these little individual tumour cells, which are most important for diagnosis in certain cancer types like colorectal cancer and other solid cancers as well. So in this way, basically we can now provide almost real-time virtual immunohistochemistry based on these amended cyclogans, which is really useful. So, in conclusion, like the use of a structural preserving deep network is key for these cell translation tasks or on pathology images. And if you add that mid-cycle loss to a cyclogan, then you can improve the accuracy and allow stain translation to take place. And we hope that these virtual IHC techniques can reduce the time and complexity of providing IHC to every patient and improve the accuracy of things like. And we hope that through this we can also unlock more opportunities for research as well. So thank you for everyone for listening, and we published a preprint on this if anyone's interested in more detail about our approach and how we evaluate it. And I'm happy to take any questions.
There's time for one or two questions. There's one at the back from Abdul.
Thanks a lot for the nice presentation. I just have one question regarding the generator of the GAN or the cycle GAN. So what type of architecture that you used, and what type of loss function that you use for the generators? And have you, because you actually concentrated more on the adding, loss, mid-cycle loss actually improved the result. What about the architecture? Have you noted that actually changing that is critical?
Yeah, no, that's right. So I'll just try to keep everything within 15 minutes, but we have explored various architectures with the original cycle GAN, and we found varying levels of success. Like the images I showed you, fairly bad ones, but in all of them, we also found the state to be patchy and a bit, inaccurate. So we never really found a solution, although it's kind of almost infinite search space. We didn't find a solution that just, where you change the architecture and make it accurate enough without actually having some, addition to the loss function to ensure the network maintain that accuracy through the translation process. Yeah.
Okay. Are there any more questions?
Hey there. I was curious if you considered framing this as like an image colorization problem, because, well, I guess it's...
No, that's all, but we've looked into that, and that's why we were trying to find, various approaches to do it, but that was the one we settled on. We didn't explore that very much.
Yeah.
Thank you.
Okay, I think we are running a bit over time, so maybe we can ask the rest of the questions to Chris himself. One more round of applause to Chris.